Okay, so now it's time to begin the session. So are you ready, Dr. Arafani?
Hi everybody.
Okay, so could you now share your screen?
Sure, I will do that. Let me. So can you see it now?
It's not visible yet. Okay, now it's visible. So
okay,
now I
great.
think you can turn it into the full screen. Okay, great. Okay, welcome everyone. So this is the cosmology session 11A of PASCOS. So the first speaker is Dr. Arafani, and she will be talking about primordial black holes in the exclusion set theory. So the talk will be for about 15 minutes, and I will update you before 3 minutes. And there will be discussion for 5 minutes. Okay.
Yeah, thank you so much.
Okay,
hello everybody. Yeah, hello everybody. First of all, I would like to thank the organizers for giving me this opportunity. I hope I could be in Korea once more, but it seems that it's not the case right now. And I hope we can get rid of the pandemic as soon as possible to meet each other in the in-person conferences. So as mentioned, I'm going to talk about primordial black holes formation, the exclusion set theory. So I will explain briefly about how we can form primordial black holes and also different mechanisms that we have for them. I'm going to explain Press-Chester formalism because it's the famous formalism for primordial black holes formation. And then I'm just going to compare what's the difference between this formalism and exclusion set theory and how we can use the method of the exclusion set theory in the case of the primordial black holes and which aspects we should change for having their formation. And at the end, I'm going to conclude. Most probably, you know that topic of the primordial black holes is becoming really hot after the discovery of the gravitational waves. But before that, also there were people interested in primordial black holes as a candidate for dark matter, because as you know, for candidates for dark matter that we know with many observations like the rotation curve of the stars and the galaxies, with lensing and also bullet cluster and also with the CMB, we already know that if dark matter should be in the form of the particle physics, it could be stable, neutral in a sense that not having the electric charge and also not having the QCD charge, should be weakly interacting, and also any candidate for dark matter should give us the right relief density that we see by the observation, especially by the CMB data. However, all the candidates in the standard model of the particle physics, as we know that they cannot fulfill these properties, so we need something beyond the standard model of particle physics. So there were some candidates like axions, Australian neutrinos, WIMPs, and some of them are still a candidate for dark matter. But as you know, for all of these, you need something beyond the standard model of particle physics. However, in the case of the primordial black holes, you just need a normal cosmology. I can say the standard model of cosmology. So the primordial black holes are the black holes that they can form in the framework of the standard model of cosmology. I'm going to tell you how we can form them and how they can be the candidate for dark matter and which properties they should have. The main difference of the primordial black holes and the astronomical black holes is that for the astronomical black holes, we need a star that have a specific mass to collapse to form a black hole. But the point is that in the case of the primordial black holes, so we don't need that star collapse gravitationally. So this means that primordial black holes can have any masses. And then the mass of the black hole is proportional to the time that black hole is going to form. And we know that, for example, if the black hole forms 10 to the minus 20 seconds after the Big Bang, its masses should be order of 10 to the 15 gram. And it's going to be clear why I'm just normalizing to the 10 to the 15 gram. Just keep in mind that one solar mass is the order of the 10 to the 33 gram. And also these relations shows you that, for example, if you have the QCD phase transition, you will be able to form black holes almost of order of the solar masses. That these are one of the candidates of primordial black holes in the observations of the LIGO Virgo, because we know that they have mass, at least the first observations have the masses really close to the solar masses. So since primordial black holes are really tiny, that invokes Hopkins to study their quantum effects, and he realized that the black holes are going to evaporate, and the temperature of the evaporation is proportional to the inverse mass of the black hole. So this means that if you have a black hole with higher masses, they are going to emit the hadrons that they have. They are going to emit the massless particles. If they have lower masses, they are going to emit, for example, the hadrons. So then by the particles that primordial black holes are going to emit, we have a really strong concentrations on the abundance of the primordial black holes with respect to their masses. And since primordial black holes, they evaporate, they are going to have a lifetime, and the lifetime of black hole is proportional to the mass cubed. So for example, as a human being, if you have a chance to convert to a black hole, you will evaporate completely in 10 to minus 12 seconds. And that's why I use this normalization of the 10 to the 15 gram in the equation of the mass, because it says that if you have mass larger than 10 to the 15 gram, which is close to the mass of the Mount Everest, says that the lifetime of the black hole is larger than the age of the universe. So these kind of the black holes with mass larger than 10 to 15 gram, they could survive, and they could be a candidate for dark matter. So the question is that why primordial black holes are useful? Of course, one can answer this question by categorizing primordial black holes with respect to their masses. If they have mass less than 10 to the 15 gram, then this means that they have already evaporated. So we can see the amount of the particles that we have, for example, with the cosmic rays, and also the coming from our galaxy and outside galaxies. So we can also say that the ones that they have mass larger than 10 to the 15 gram, they could be a candidate for dark matter because they could survive. And also recently, by the observation of the LIGO and Virgo, they could be a candidate for the gravitational Virgo DC. And the ones that they have mass over the 10 to the 15 gram, you can see their effects with the cosmic rays that we have. So the concentration with respect to their masses is really high. So since primordial black holes are useful, how we can form them? There are different mechanisms. One of them is by the density fluctuations that rise by inflation, because we know that the inflation is the seed of any structure formation. So why not primordial black holes? There are other mechanisms, for example, the soft equation of the states, for example, in the phase transitions in the early universe, for example, the electroweak phase transition, QCD phase transition. Since the equation of the states becomes softer, then it's possible to form primordial black holes. There are also different mechanisms like bubble collisions that says that even in the phase transition, you make the bubbles. So there's a chance that these bubbles collide each other and then they form primordial black holes. But I'm just going to focus on the effect of the inflation on primordial black holes formation. One of the famous formalism for primordial black holes formation is the Press-Cheshire formalism, which is the formalism for the formation of any compact object, in our case, primordial black holes. This formalism tells you that if you have a density perturbation with respect to the space, this density perturbation has any specific threshold, which this threshold is different for any compact object, that region has a chance to collapse to form that compact object. So it tells you that if this distribution should be Gaussian, then you can really use simple formula saying that the fraction of the region with the mass larger than m, which should collapse to form a compact object, is going to be given by the probability distribution function of the perturbation. So delta is the density contrast of the perturbation, and m is the mass of the region with the size r that's going to collapse. So you need to pass a threshold delta c up to the infinity, because we are going to see that with the Press-Cheshire formalism is really falling function. So it doesn't matter you put this upper bound to infinity or 1. And then the gamma says that the whole mass of the region is not going to collapse to compact object. So you should have a factor of that. So if you have a Gaussian distribution function, it is really simple. So you have the probability distribution function in this form. The delta is giving you the density contrast of the density perturbations, and also sigma is the variance of the density perturbation. So where the effect of the inflations comes around, it tells you that the power spectrum of the density perturbation is proportional to the power spectrum of the curvature perturbations. And we know that the power spectrum of the curvature perturbation, if it comes from the inflation, is in the power law form with the spectral index of n. And sigma is the variance that for the variance, you need to smooth it by using a window function, and that you can use different one. For example, you can use the Gaussian window function or top hat, whatever is really useful for your studies. And you see that in this equation, everything is the function of the mass, but we have everything in the function of the R, so we should just find the relation between the mass and the scale that's going to collapse, and the size of the region that's going to collapse to this compact object. So everything is in hand. You should just put in this formula, and you are going to find the relation for the abundance of the compact objects, in our case primordial black holes, because we are choosing the density contrast to be 0.47 in the case of primordial black holes. And then what you are going to get is the value of the spectral index for forming the black holes with any specific masses. So this is the final result. Please look at the blue curve. That tells you that if you want to have the fractions of the black holes, this F is exactly this parameter beta that I explained. It tells you that if you want to have black holes with mass larger than 10 to the 15 grams, so you can fix the parameters and solve the equation, and you can find the value for the spectral index in the scale of the black hole's formation. And that it shows you that the scale of the black hole, the value of the spectral index in the scale of the primordial black hole's formation with mass of order of the 10 to the 15 gram, to be a candidate for dark matter in the Gaussian distribution function in pressure formalism should be at least 1.4, which is much larger than the spectral index, the power spectrum, the spectral index that we have by the observation of the CMB, because we know that by the observation of the CMB, this value is of order of the 10 to the minus 10, but what we got is of order of the 10 to the minus 2. This means that in the scale of the black hole's formation, we really need to have really high power spectrum. So the question is that how we can form them. But this beta, or parameter F, is the fraction of the black holes in the time of their formation. We need to find the fraction of the black holes right now if they want to become a candidate for dark matter. So the FPBH in general is the fraction of the parameter density of the primordial black holes with respect to the dark matter. So this parameter F could be 1 if the black holes with any specific mass could be the whole dark matter. So let's see how what we have by the observations regarding this parameter of the F by observations. For example, in the case of the gravitational wave studies, we know that there are different observations like Kepler, HSC, Ogel, Eros, and modules, which is the really all the observations. And then these observations categorize that in any specific mass ranges that we can consider primordial black holes as a lens of the gravitational lensing, how much fractions of the dark matter could be in the form of the primordial black holes. And you see that we have the values of order of 10 to the minus 2 and 10 to the minus 3. So I'm going to focus in these gravitational lensing studies and also the gravitational wave result that comes by LIGO and Virgo. And LIGO will go put a concentrates of order of the 10 to the minus 2 with the masses of order of the 0.2 solar masses up to the 1 solar masses. But in the fraction of the primordial black holes as a candidate for dark matter with respect to their masses, there are still gaps, means that we don't have any well-defined observational results. This means that they are observational results, but they are really model independent. Depends on that how you form, how you, for example, structure your galaxy and also the other model buildings that you made as. So there's a mass range that we call it asteroid mass range of order of 10 to the 16 gram up to 17 gram, which is still allowed to have the whole primordial black holes, whole dark matter in the form of the primordial black holes, and other different masses like sublunar mass ranges, intermediate mass ranges of order of 10 to the 10 solar masses up to the 10 to the 3 solar masses, and also really, really large black holes of order of the 10 to the 11 solar masses. So these are the regions that we already don't have really confirmed observational data, although there are debates in the community regarding these mass ranges. So I explained about the pressure formalism, so I'm going to focus on the idea of the exclusion set theory. As you know, the exclusion set theory is a really good method to form a formation of the halos in cosmology. It tells you that if you have the delta, which is respect to the variance, because S here is the square of the variance that you have, this tells you that if you consider your perturbation as a random walk, and considering that this random walk perturbation should pass a threshold, in our case, 0.47 for primordial black holes formation, if these perturbations pass a threshold, then in this trajectory has a chance to form to collapse to form a halo. But in the case of the primordial, but in the case of the primordial black holes, what we have changed was that because the black holes form when their scales enter the horizon, Having a large S means that you are going to have a smaller scale. So then the small scale should enter the horizon sooner than the larger one. So instead of having the first up crossing idea of the pressure exclusion set theory for the halo formation, we introduced new first touch event, saying that since black holes should enter to the horizon with the scale sooner than the larger scales, so we introduced the first touch idea, and then we follow the trajectory of these black holes to see that if there is a chance for these first touch trajectories to form primordial black holes. So if it's a really statistical formula, then this number of these trajectories is going to give us an idea about the number of the abundance of the black holes with that specific mass that they're going to form, because S is proportional to the mass that's going to collapse. So that's the idea of the exclusion set theory. We just modified it with the idea of the first touch instead of the first upcrossing idea. The plots that you are seeing here is close to the ones that we have for the Press-Chester formalism. You see that it's the falling function is exactly the same as the Press-Chester formalism. And also we try to show that counting the first upcrossing and also first touch in the observation is not going to change that much the fraction of the black holes, but of course the first upcrossing ones give us the more primordial black holes than the first touch ones. So then we also studied that how the value of the spectral index should change with respect to any specific mass for primordial black holes, and we count all these trajectories that they can pass this threshold to form a black hole with specific masses. So the final result is that for all the mass ranges that we have by the gravitational lensing, by the gravitational waves, and also the mass ranges are still they don't have a confirmed constant rates. We try to compare the value of the spectral index that we find with the Press-Chester formalism and the EST formalism. You see that the numbers are really close to each other. But the point is that in the case of the exclusion set theory, formation of the primordial black holes is much easier than forming by Press-Chester formalism, because in Press-Chester formalism, you really need to have a high peak of the perturbations in that specific range. But in the case of the EST, since it's a statistical formation of primordial black holes, you are not really worried about that. You just need the new trajectories that you form passing that threshold value. So the results are really similar. I cannot really say that the difference of the order of, for example, 10 to minus 3 really makes sense in this case, but it can be helpful to form primordial black holes in the EST, and also trying to study the merger and also the accretion of primordial black holes in the EST formalism that we are going to do in the future. Yeah, and then the conclusion, I just try to explain that the fluctuations that rise by inflation are the most likely source of primordial black holes. The power spectrum that we need for primordial black holes should be much higher than the value that we see by the observed scales of the large scale structure and the CMB. And we can form primordial black holes in the EST, in exclusion set theory, with any masses, which is not the case in the Press-Chester formalism. And our studies shows that in any mass ranges, primordial black holes cannot be the whole fraction of the dark matter. So the claims that at least comes by the observations that sometimes primordial black holes could be a whole dark matter cannot be true, because in the case of the EST, we cannot get that in this form. So thank you for your attention. I will be happy to answer for any questions that you have.
Okay, so any quick questions? We have some couple of minutes for questions. So if you have any questions, please turn on your microphone and just speak.
I don't see the chats if there is any question there.
Okay, then I have one question. I am a little bit missed, but could you please remind the bottom line why the exclusion set theory excludes the whole dark matter as the primordial black holes?
It depends on which mass ranges you are looking for. For example, we try to show that, of course, even for the really large masses of order of 10 to the 11 solar masses, it's possible that the fraction of the primordial black holes should be 1, means that the whole dark matter. But the spectral index that you really need for that is really, really high. So it's not really reasonable to say that if you are going to have a linear perturbation theory, this high spectrum, because you can convert this spectral index to the power spectrum. So the value of the power spectrum should be really, really larger than we expect. So we don't expect that to see even this large power spectrum in the scales of the black hole formation. You can find the black holes.
So it essentially is
not
kind
really
of seesaw between the low mass bound and the spectral index at the corresponding scale.
Yeah, exactly.
Okay, thank you very much. So any questions? Okay, if there is no question, then let's thank Dr. Fanny again. Thank you.
Thank you so much.
Okay, I see still we don't have the second speaker, Dr. Lostami. I see no. So for the sake of the progress, I think first we have to skip the second speaker and we just directly go to the third speaker, Dr. Jeremy Offenja. Dr. Offenja, are you available for your presentation?
Yes, can you hear me?
Yes, it's very good. So please share your screen.
Good. Okay, so let me share my screen. How do I do that? Okay, and this is okay. So you should see my first slide.
I saw that the Rostani is in long parallel session. I will tell him that to move to this session, but you can go on. I mean, you can replace the position.
Okay, so let's first proceed, and the third speaker then will be the second speaker. Okay, so the next speaker is Dr. Jeremy Offenja, and he'll be talking about dark matter and dark radiation from primordial black holes. So you have first 15 minutes, and then there will be questions, okay?
Okay. Thank you. So first, I would like to thank the organizers for allowing me to do this parallel session. And I would also like to thank the previous speaker to speak about primordial black holes because it gave a really nice introduction to my own topic. So thank you. I will speak about dark matter and dark radiation from primordial black holes. So constraints on these two aspects of the dark sector. In the early universe. So it was a work done in collaboration with Isabella Massina, Giorgio Orlando, Alexandre Arbet, Pearl Sandik, Barmak Shams El Aghi, and Kuversinia. So it's two different papers. And so let me begin with my introduction. Then I will speak about, in order, warm dark matter constraints and then dark radiation constraints on primordial black holes. So we all know about the missing dark matter issue in cosmology and astrophysics. So there are many candidates proposed to explain the missing mass of the universe, one of which is primordial black holes. So this is not the hypothesis I will follow in this talk. In fact, I will consider black holes that have already disappeared, so that cannot constitute dark matter, but which gave rise to some dark sector particles through evaporation in the early universe. So this is the canvas of my talk. Okay, so primordial black holes are black holes formed in the early universe. So there is a link between the time of their formation and their mass. And there are many motivations for their existence, one of which is the results of the merger measured by LIGO-Virgo collaboration and other aspects of observation, recent observations. And one striking aspect is that we still have some unconstrained mass ranges for primordial black holes, some of which allow them to form dark matter. But the one we will focus on is the really light primordial black hole masses, so below 10 to the 9 grams. And in fact, in this mass range, primordial black holes are for the moment unconstrained because they are believed to have evaporated before Big Bang nucleosynthesis. So they didn't have any impact on cosmology or astrophysics apart from the really early universe. So there are no constraints on them, and we will try to put some constraints on them in this talk. Okay, so primordial black holes are subject to Hawking radiation because they are really small. So their Hawking temperature is really high, so they can emit a lot of particles with some kind of a thermal spectrum, which is given by this equation 3. In fact, the spectrum is close to the black body spectrum. You can recognize the Boltzmann factor at the denominator. And on the numerator, there is an additional factor different from the black body one, which is called the gray body factor, and which encodes some particle spin dependence in the Hawking radiation and some correction to it linked to the possible spin of primordial black holes. So the rate of emission of particles depends on the particle spin and on the spin of the primordial black hole. Then you can stack the spectrum of Hawking radiation through the whole black hole lifetime, and you obtain some stacked spectrum at the end of the black hole evaporation, which gives you an average information about what the black hole has inserted in the early universe at some time. This is some quantity we will use. To compute the Hawking radiation in these two papers, we have used the public code Blackhawk, of which I am one of the authors. And one interesting aspect about this code is that it is currently updated. It's a major update that will include some really striking new features, one of which being the possibility to emit dark matter or dark radiation particles on top of the usual standard model spectrum. So this gives access to a whole window of new studies about dark matter and primordial black hole mixed studies. Okay, so you can download the code on the HelpForge at the address mentioned there. So first, we will talk about warm dark matter constraints, and I will present the hypothesis of this work. So we consider that there were primordial black holes with a mass below 10 to the 9 grams, so unconstrained because they evaporated before BBN. Then we consider that there exists a dark sector, which is emitted at the same time of the standard model because of Hawking radiation by primordial black holes. We consider only one light particle, so with a mass in the MEV range, so it's the range for warm dark matter. And we are agnostic about the spin, so it can be 0, 1, 2, 1.5, or 3.5. And it has no interaction with the standard model over the gravitational. We will consider both radiation and domination, radiation and matter domination in the early universe. So either the universe is dominated by radiation or it is dominated by primordial black holes if they were sufficiently abundant when they formed. And we will place constraints on primordial black holes linked to the fact that they emit warm dark matter, because we know that we have warm dark matter constraints through structure formation, for example. And we will use what we call the transfer function of phase space distribution of warm dark matter to put constraints on this and then on primordial black holes. So first, this is the spectrum of particles, dark matter particles emitted by Hawking radiation from primordial black holes. So on the left plot, you can see the instantaneous spectrum, which is rescaled, so it is not mass dependent of some particle spins. And you can see that there is a strong dependency of the spectrum of emitted particles in the particle spin. So if you have a higher particle spin, then you have a lower emission rate, which is up to 2 orders of magnitude below the spin S equals 0 case. On the right plot, you can see the stacked spectrum, which is also rescaled to give something we call the PSD, phase space distribution. So it's a momentum distribution, and you can see once again that when you increase the particle spin, then the emission rate decreases, so the PSD peak decreases. We have computed this stacked spectrum with 2 hypotheses. So the first is radiation domination with the maximum possible fraction of primordial black holes to still have radiation domination. The other one is full black hole domination. And you can see that this modifies the low momentum tail of the distribution, but this doesn't modify strongly the peak of the distribution. In fact, the PSD, which was calculated with Black Hawk, can be then given to another code, which is class. And this can be used to derive what we call the transfer function of a matter spectrum. And on these plots, you can see this transfer function. So on the left plot, we plotted the transfer function for the different spins for m equal 1 gram black hole. And we compare it to the transfer function for usual warm dark matter candidates. So with a mass of 110 eV, which is already excluded by small scale structure constraints. And in fact, small scale structure constraints give a lower limit on the mass of warm dark matter, which is this mass of 3 keV, which is represented as a pink line on the left plot. And you can see that with our hypothesis, either with radiation or matter domination, all the transfer functions are below the 3 keV line. So all these transfer functions are excluded by warm dark matter constraints. So we cannot have these results for primordial black holes. And in fact, we can deduce that full black hole domination is excluded and beta equal to beta bar, so maximum radiation domination is excluded also. On the right plot, we plotted the same results, but for the spin s equals 0 only, not to crowd the plots. And we diminished the initial abundance of primordial black holes until the transfer function is above the 3 keV line. So until we are not excluded by warm dark matter constraints. And in fact, this can translate in a constraint on the abundance of primordial black holes with a certain mass below 10 to the 9 grams. So on the last line of these plots, you can see that the warm dark matter constraints give beta constraints on the abundance of primordial black holes for all spins, so 0, 1, 1/2, 3/2, and 2. From these constraints, we can deduce what would be the mass of the dark matter, warm dark matter particle from primordial black hole evaporation. This is only proportionality constraints between the abundance of dark matter today and the integral of the PSD. So you can deduce the mass of the dark matter particle. Okay, so this was the first constraint. And then let me move on to the dark radiation constraints. So for this study, the hypotheses are the same. We consider black holes with a mass below 10 to the 9 grams that evaporated before BBN. We will consider this time spinning black holes, and we will see why. And we assume that the dark sector particle is the spin 2 massless graviton. And in fact, this will act as some dark radiation in the early universe. So we computed the dark radiation with Black Hawk again, and then the constraints are obtained through the delta N effective, so which is the effective number of neutrino species in the early universe, which is constrained by both CMB and BBN observations. So we consider spinning black holes in this particular study because it is believed that if black holes form in the early universe during an early matter-dominated era, then really strong processes during their formation can give them a really high spin. So first-order effect, which is the non-Gaussianity of the I would say overdensity repartition will give a really strong spin to the black holes formed during this era. And the second order effect is linked to the non-uniformity of the distribution of mass inside some collapsing shell. This is the second order effect, which is most of the time below the first order effect. And another possibility is that primordial black holes acquire spin through mergers between them. So this could be the case if they are sufficiently numerous and, for example, clustered when they form. We'll consider these two hypotheses. So we can see on these plots the delta N effective, which is computed integrating on the whole dark radiation emitted through the black hole lifetime and redshifted to the CMB and to BBN. And we can see that for black holes, for full black hole domination, if black holes follow the spin distributions of which I just showed you, you can see that if the overdensity power spectrum width is low enough, so if the primordial fluctuations is sufficiently peaked, then you can have current CMB constraints on these distributions, which you can see on the left plot. And on the right plot, you see that the second order effect is at present unconstrained. But as you all know, there will be in short time the CMB stage 4 experiment that will reduce a lot the sensitivity, that will increase a lot the sensitivity on delta N effective for the CMB observations. And you can see that both these hypotheses are completely excluded by CMB stage 4 experiments. This is really interesting, in fact, for the near future. Considering high spin black holes, which I just mentioned, if you have really high spin black holes, so monochromatic distribution of high spin black holes, then you can see that the full black hole domination is already excluded for masses between 10 to the 8 and 10 to the 9 grams. So this is a new constraint that didn't exist in the literature. And you can see that if we increase the spin more, then we saturate to some value of delta N effective, and it is not interesting to go beyond this value. On the right plot, you can see the exclusion limits on the primordial black hole spin, depending on the mass for the near future stage 4 experiments. So what we can see is that if primordial black holes had a spin below 0.69, then stage 4 will not be sensitive to them. And if they had a spin above 0.81, then the whole mass range will be excluded by CMB stage 4. So this is really interesting. Okay, so let's move on to my conclusion. What we learned in this talk is that using a mixed model of primordial black hole and dark sector, either dark radiation or warm dark matter, we can put constraints on the abundance of primordial black holes in a previously unconstrained mass range, so the 10 to the -5 to 10 to the 9 grams. So black holes cannot represent dark matter in this range, but it still puts some constraints on their formation, because if they didn't exist, that means that the early universe models should account for this non-existence of primordial black holes. So the last thing I would like to say is that Black Hawk, the public code Black Hawk, will be updated really soon. So keep in touch with that, because the new features will be really interesting for a whole kind of different studies. Thank you for your attention. And if you have any questions, just ask them.
Okay, thank you. So if you have any questions, please turn on your microphone and speak. Any questions?
Well, I have a question or comment. So this signal is visible only when the primary black holes dominate the energy density of the universe, right? And then in such a situation, maybe black holes may merge together, or and then emit gravitational waves also. So in that sense, there may be some other delta ineffective contribution also from gravitational waves. So it may be more non-trivial to draw information from delta ineffective. Do you have some comment about that?
Okay, so you are speaking about the dark radiation constraints, I expect. Yeah, so in fact, yes, you're right. If PBH are sufficiently numerous, if they dominate the energy density, then we expect mergers. So in fact, these mergers will be associated with gravitational waves. We also expect that when the primordial black holes fully evaporate, then this causes a dissipation of their energy density, which will induce gravitational waves also. And these two aspects are in fact already discussed in the literature. So I could refer you to some papers about that if you want. And in fact, it's not quite linked to dark radiation. These dark radiation constraints are associated with really high energy hot gravitons that give a lot of energy in the early universe. The gravitational waves you are talking about have a lesser energy because their frequency is really smaller. So it will not give contribution to dark radiation, in fact, not sizable. It will give a contribution to the gravitational wave background today.
Okay, any other questions? So I have one very simple question. So just taking a look at these graphs or in the previous pages, there seems some jump around the primordial black hole of mass 10 to the 8 gram. Is there any reason, or I just missed you explained the reason?
Sorry, I didn't hear your question.
So if I just take a look at these graphs or the previous page, there's a jump around black hole mass of 10 to the 8 gram or something like that. Can you explain the reason, or simply I just missed the reason you explained?
Okay. So in fact, as we consider that black holes dominate the energy density of the universe, we also consider that their evaporation gives the full reheating. So their density, depending on their mass, is fixed. And then we don't have a choice on the density of primordial black holes. So you would expect that the amount of dark radiation, as it is only a proportional to the primordial black hole density, is also fixed, and you would expect a straight line, an horizontal line for the delta N effective constraints. In fact, there is in the formula used to compute, I can show it to you, used to compute this constraint. So it is on this page. You can see in this equation 2 that you need to take into account the number of degrees of freedom, of relativistic degrees of freedom between reheating and matter radiation equality. And in fact, depending on the black hole mass, you have a different evaporation time, which corresponds to a different reheating time. And then this changes these ratios between effective number of degrees of freedom. And this is the only reason why we have a jump. Otherwise, we would have a straight line with less than 1% precision.
Okay, great. Thank you. So is there any further questions? Okay, so if there is no more questions, let's thank Dr. Alfingda for the great talk. Thank you very much.
Thank you.
Okay, so now the shuffled speaker will be speaking. So the next speaker was, well, originally it's the second speaker now, but now is third speaker, Dr. Asabat Lostami. And could you please share your screen?
Hi, have you my screen now?
Yeah, it's very clearly visible.
Okay, sorry,
so pop up.
Let me share it. Yes, it's my presentation, I'm sorry.
Okay, great. So Dr. Lostami will be talking about effective field theory and primordial black holes. So you will have 15 minutes for your presentation, and short questions and answers will be following. So please proceed.
Thank you. I appreciate the organizer for giving me this opportunity to talk here about my works. I wanted to talk about effective field theory, compatible PBAs. I mean that how a model of effective field theory, which called extended effective field theory, can give a way to produce primordial black holes, which can actually compromise a sizable fraction of cold dark matters. Let's go to business. At first, let me introduce the idea of effective field theory. As you know, sorry for you see my cursor? Okay.
It's visible.
Okay. Effective field theory idea comes from this fact that effect of high energy scales can be encoded in an infinite number of operators of higher dimension. Effective field theory of inflations comes about with noting some points to write its action. The first is that because inflation came to an end in the space-time, the time translation would finally spontaneously would be broken. And therefore, Goldstone bosons appears in this way, which they nonlinearly transform under time diffeomorphism. And in the unitary gauge, this Goldstone boson is eaten by metric. The other property of this theory is that no inflaton fluctuations can appear in this gauge because the surface of constant time and constant inflaton would coincide. Therefore, the most general action one should include in the theory should be only three diff invariant, I mean spatial diff invariants. And at third-level operators, this gives actually the standard single field slow roll inflations, but higher mass dimensional operators led to the deviation from standard inflation. There are some realizations such ghost inflation, K inflation can comes about in such models. However, there is a point which people before that thought that effective field theory with dispersion relation beyond the quartic one make the interacting operators dominating at the IR level. So this kind of dispersion relation invalidates effective field theory. But as Amjad Ashurian and his collaborators show in 2018, that extended effective field theory is okay if the unitary action renders lower order correction, which is dominated at horizon crossing, and there would be no any problem with that. For example, here I wrote the action for the extended effective field theory up to mass 4, up to mass dimension 4, which as you can see, two last lines are those which are actually were missed in the actual works. And this is what people call extended effective field theory of inflation. Using Stugelberg tricks, one can back Goldstone bosons and find a dispersion relation in terms of Goldstone bosons dynamics, which here you can see that C squared and alpha and beta, which alpha and beta are actually dependent on time, function of times, because as you can see in this Lagrangian, the coupling here, which appears here, are actually depending on time because we just pose the three different variants on the action, not for different variant. Okay. After this short introduction, let's talk about a bit about primordial black hole formation scenario. As you know, there are a host of primordial black hole scenarios, formation scenarios, which people put forward during these years. But what I care here is the collapse of overdense scenario, in which the overdense regions in the during radiation dominated era can collapse, and form primordial black holes. However, initially, the co-moving size of this over dense region is, much larger than the Hubble horizon. But when during the evolution of the universe, this co-moving size re-enter the horizon, and then when it becomes bigger than gene lengths, then it collapses and gives a primordial black holes. And this means that the density contrast for density of these regions should satisfy this relation, which calculated at the time of horizon crossing. Therefore, the PPH mass would be of order of the horizon mass. And here the gamma star factor you can see in the last relation at the time of formation. This is about 0.2. Okay. Now, inflationary scenarios, if changed in a way they can describe these our densities via primordial curvature perturbation, and then these our densities have a power spectrum or 2-point function, correlation of 2-point function, which is related to the primordial curvature perturbation power spectrums, which you can see in this relation and is well known to people. For inflationary scenario to describe primordial black holes, it needs its power spectrum to be lose his scaling invariant conditions, and it's important. It's a very important role in this construction, and this needs that the power spectrum enhanced in the scale which we want to create primordial black holes up to order 10 to the 9 based on the profile that you use in theory. Here you can see the mass of primordial black holes, which is related to the wavelengths of these over dense regions, which is related to common curvature perturbations. And by knowing the scales, you can find the mass of primordial black holes, and then let the power spectrum to be enhanced exactly at that scales. For example, from this region, this relation, you can see, for example, the solar mass PBS, the wavelengths or the scales of this kind of black holes should be e to the 20 scale of CMB. And for those of black holes that will place in 10 to the minus 17 solar mass to 10 to the 16 solar mass, which this kind of black holes can describe a sizable fraction of dark matters. We need to enhance the power spectrum at the scales e to the 65.5, e to the 2, e to the 40 scales of CMB scales, Okay, and there is a forward way to driving mass fraction for PBH that comes to side in this way, and with the assumption of Gaussianity distribution for these primordial black holes, one can calculate the mass fraction this way. Here, the delta HC is in fact a smooth density contrast at the horizon crossing, which this has been smoothed, at the scales which these densities can, our densities can collapse to form PBH. And sigma, of course, is the variance of Gaussian distribution, which could be calculated if you are given, you know, power spectrum of this density contrast. And finally, you can find the mass function, which is defined as a ratio of density of primordial black holes to the density of you know, cold dark matters. So we use this picture and try to understand how effective field theory of inflation with using of its you know, modified dispersion relation could describe primordial black holes for compensating of whole dark matters. Here, because extended effective field theory of inflation modifies the dispersion relation, one expects that every 2-point function related to the scalar perturbations need to be also modified. And the power spectrum related to this would be changed. And here we define a modulation gamma, which is the ratio of the power spectrum which coming from effective field theory, extended effective field theory of inflation to the standard Bunch, I mean Bunch-Davies. Here you can, if you remember power spectrum of Bunch-Davies, you can see here that C squared appears in the denominator, and epsilon also. It's worth to mention that you know, in some models like near inflection point inflation, people try to reduce epsilon, the slow parameters, in the scale of interest to get PBH and modify primordial black, modify power spectrum. All other models in effective field theory try to you know, modify C squared and try to change it. But as mentioned in literature, all these models actually may be in contrast with the EFT criteria. But without any need of doing such a kind of work, we can get enhancement, considerable enhancement in power spectrum with just modifying dispersion relation coming from extended effective field theory of inflation. But as you see, this dispersion relation is very complicated to calculate numerically, and you need follows 2 methods. One method is a numerical analysis, which you can put your computer and try to solve it, or other method in advanced mathematics, which they call asymptotics methods, which it could be very interesting if it could be put forward. But here we can understand this dispersion relation, how change power spectrum. You know, here alpha and beta are a function of time and of course scales. And numerical analysis show that for alpha bigger than alpha, for positive alpha, in fact, there is no enhancement in gamma. Rather, it also you know, decreases. And you can see, for example, some solutions here, numerical solution here in picture, where, for example, alpha when is less than 1 but positive, gamma actually respect to beta would decrease. But I'm also for alpha bigger than 1, this is so. But for alpha less than 0, depending on the parameter beta or alpha squared, an enhancement could happen. For example, for alpha minus 0.01 with z equal to 0.13, for example, gamma can reach the value, meet the value, 10 to the 9. And it's very suitable for creating parameter black holes. Here, for example, you can see for alpha minus 0.01, here show how gamma changes with respect to the parameter z. So for giving the primordial black hole, sorry?
Time is almost up. Please wrap up.
Oh, thank you. Just a minute. Here we adjust a parameter alpha respect to time that is positive in some in some scales, and then become negatives in scale of interest, and then back to its positive value. And this results that gamma actually peaks in the scale of interest. And here I show that the result mass function of primordial black holes related to this construction here for a PBH from 10 to the minus 17 to 10 to the minus 13, which can compromise all dark matter that you can see here in our model. Okay, let's wrap up this talk. Our conclusion: PBH may form through the collapse of our density regions, inflation or scenarios with a non-scaling variant. Power spectrum can use to for PBH formation, and extended effective field theory of inflation with higher order corrections, which goes beyond the quartic order, is one of candidates. A sixth order dispersion relation, which we use here and coming from the extended effective field theory of inflation, has power spectrum at arbitrary scale with arbitrary amplitude. Thank you.
Okay, so probably one single very quick question. Okay, I have one question. So if the enhancement is of the power spectrum is very great, then usually I would be worrying about the unitarity of the theory. So is it okay for the extended effective field theory of inflation context?
Yeah, of course. There is no any problem with the extended effective field theory of inflation. The unitarity would be conserved. And there is no problem. All thing you should be worried about is, in fact, EFT compatibility. EFT compatibility.
Probably that's better wording. Okay, so if there's no more questions, let's thank Dr. Lostami again. Thank you. Okay, so the last speaker of the session is Dr. Marcos Garcia. So, Dr. Garcia, could you please share your screen?
I'm trying. It says that Avasal needs to stop sharing first.
Okay. So, Dr. Lostami, could you please now turn off sharing your screen?
Yes, I'm sorry.
Yeah, first you have to do that.
All right.
Okay. Probably now you can do it now.
Yes. That should be working,
Great.
I think.
Great, it's working. So you have 15 minutes and questions and answers will be following. Okay, so the last speaker of the day is Dr. Marcos Garcia, and he'll be talking about dark matter and reheating. Please.
All right. Well, thank you so much for the introduction and for the opportunity to talk. My talk is the odd one here because I'm not going to be talking about primordial black holes. I'm instead going to try to motivate the study of dark matter production during reheating by means of an example. And this example is that of a spin 3/2 dark matter particle, described by the Rayleigh-Schwinger Lagrangian. Conceptually, of course, there's really not a lot new about such a proposal, which has been explored many times in the literature. In particular, you can think of supergravity models, for example, classical gravitino scenario. But nevertheless, that one and many other proposals insist on working with a WIMP-like stable dark matter, and that requires typically some high degree of symmetry. So let's now do something in the completely opposite regime, let's say, and consider just a very minimal setup. So just take the standard model with an extended neutrino sector to generate the light neutrino masses. So nu r is the right-hand neutrinos, and we add to it the only Lorentz and gauge invariant operators that would couple a spin-free half particle to standard model fields and to the right-handed neutrino, at least at lowest order. So this first operator will couple dark matter to the abelian gauge boson and the right-handed neutrinos, while the second one would couple it to the Higgs and the SU2 charge leptons. And these two arising couplings, alpha 1 and alpha 2, are at this point completely free. Now, if the first operator somehow dominates, let's say due to some hierarchy, then one can compute the corresponding scattering cross-sections. They turn out to be suppressed and lead to a scaling that goes with the fourth power of the center of mass energy. So this suppression is essentially coming from, of course, the Planck suppressed vertex, the heavy mediator, the nu r, and this empty half contribution from the dominant helicity 1/2 component at high energies. So cross-section, as I said, grows with the fourth power of the center of mass energy. Also, without the addition of this ad hoc symmetry that I mentioned before, we cannot have a stable dark matter particle, and so it will eventually decay, in this case by means of 2 and 3 body processes.
Excuse me, your screen is not moving at all?
It's not moving at all.
Yep.
What do you mean? So I'm still stuck in the first slide?
Yeah.
Okay, let me stop sharing then, because that shouldn't be happening. 1 second. Okay, so let me try to do that again. Share screen. Here, share. Might be a problem with the PDF.
Could you please
reader.
go back and forth a little bit?
Sorry, 1 second. So it's full screen now. Does it change now, or is it still stuck?
Still, we are waiting for the screen to show up. We just, yeah, now.
Maybe I can't use the.
Yeah. Can you just go back and forth for a while? Let's
see. So does it work now?
Yep. Now it's moving.
Okay.
Great.
Yeah, it's probably an issue with the full screen thing. So let me keep the edge here. That'll make it work. So anyway, so I was already ahead by a couple of slides. Let me skip this part. I just introduced the model the particle content. Sorry. And I was talking here. So essentially referring to this operator that couples dark matter to right-hand neutrinos and gauge bosons. So as I said, there is suppression in the scattering production cross-section that goes with the so that it goes with the fourth power of the center of mass energy below the energies comparable to the mass of the heavy mediator, and this dark matter particle is unstable, so it decays to 2 and 3 body processes. These 2 body process in particular is quite valuable because the resulting signal contains a photon and neutrino monochromatic pair with an energy given by 1/2 of the dark matter mass. Okay, and the lifetime, of course, depends on the coupling and the masses of the neutrinos and the dark matter. Now, if this second operator that couples dark matter to Higgs and leptons dominates, the cross-section grows now only, say, with the second power of the with the squared yes of the center of mass energy, and both the production and the decay processes are somewhat more difficult to analyze, but of course it can be done. Main thing to notice is that in both cases, for both operators, the cross-section is an increasing function of the center of mass energy, implying that this dark matter particle is necessarily produced when the primordial plasma present in the early universe was the hottest, which means inflationary reheating. Furthermore, assuming that the inflaton phi is only coupled to the right-hand neutrino, this dark matter particle will be produced directly from the decay of the inflaton via three-body channel if this nu r is lighter than the inflaton, or through loops if the opposite is true. So all in all, we definitely need to look at reheating to determine the relic abundance of these spin-3 half dark matter. And to do that, then let me briefly talk about some generalities of reheating. So as a reminder, reheating is the period of time that immediately follows inflation, during which the inflaton oscillates about the minimum of its potential and it decays. Now, reheating is far less constrained than inflation, that must be said. So this picture is showing a family of potentials, which are known as the T attractors, all of which lead to essentially the same form of the power spectrum, but which behave very differently during reheating. So in fact, you can parameterize the minimum about which the inflaton oscillates as a monomial. So the usual scenario would correspond to a quadratic bottom, but quartic or higher order potentials are perfectly allowed by the data. And of course, as you can imagine, the dynamics of the inflaton will depend on the shape of the potential. So for a quadratic bottom, the oscillation of the inflaton is harmonic with a decaying envelope due to expansion, while for other potentials, the motion is anharmonic, resulting in the well-known fact that the quadratic oscillations mimic a matter-dominated era, while a quartic bottom mimics a radiation-dominated epoch. Now, when we couple the inflaton to matter and radiation, things complicate a little bit more because one now needs to solve a system of coupled Boltzmann equations where the relativistic decay products, denoted here by R, are going to be populated with a rate that depends on the coupling to the inflaton field. So here, for example, the inflaton is coupled to a pair of fermions, and therefore the decay rate has this very simple form. This is just nothing but a Yukawa coupling. But this mass parameter is not necessarily a constant. Okay, it corresponds to the curvature of the minimum of the potential, which is constant for a quadratic potential, but is a function of time for a non-quadratic one. And what this plot is trying to convey is precisely the fact that for a quartic potential, the inflaton decays much more gently than for a quadratic one. So here the decay is exponential, here it's power law. And this is also dependent on the final state of the decay, because now if the inflaton decays into a pair of bosons, then the mass parameter appears in the denominator, and actually a flatter potential leads to a more efficient reheating. So anyway, to get to the point, the reason why reheating is crucial to determine the dark matter relic abundance is precisely because the temperature of the relativistic plasma evolves during reheating. So here, assuming for simplicity that the thermalization is instantaneous, the temperature of this plasma will rise very quickly after inflation ends to a maximum temperature, and then it will decrease with a gentle slope until the inflaton is depleted at T reheating. These slopes are, of course, dependent on the potential and will determine when dark matter is produced, because it might be produced around T max or around T reheating, depending on the steepness of the cross-section as a function of the energy and how efficiently the inflaton dilutes any previously produced dark matter. And even more, of course, I mentioned here instantaneous thermalization, which is not quite a correct thing to say, because it takes time for the decay products of phi, which are initially produced with an energy of the order of the inflaton mass, to populate a soft thermal bath from collinear radiation emission that eventually will thermalize the whole plasma at a time scale that is dependent on the coupling, in this case, a gauge coupling that controls the elastic and inelastic processes that lead to kinetic and chemical equilibrium. So as I will mention now briefly, all these effects are going to play an important role. So having talked about reheating, now we can proceed to solve the Boltzmann equation to determine the phase space distribution and hence the abundance of these spin-3 half dark matter. Now, the suppression of the cross-section implies that these dark matter will be produced outside of thermal equilibrium. It will never thermalize with the radiation bath nor with itself. So that is the freezing scenario. And hence only forward processes and the phase space distribution of parent fields need to be taken into account to determine the phase space distribution. So, for example, if one considers the decay of the inflaton into a pair of dark matter particles, the amplitude corresponds to the loop diagram that I just showed, while the phase space distribution of the inflaton is nothing but that of a classical condensate at rest, meaning that, so this equation can be integrated exactly at early times, and the corresponding phase space distribution of dark matter looks like this, or actually any relic, in fact, in the absence of equilibrium. So it scales with the negative 3½ power of the momentum, and it has a sharp cutoff due to the fact that the dark matter cannot be more energetic than the inflaton is massive. Now, this curious distribution is going to evolve during reheating, and it will eventually acquire a Gaussian tail after most of the inflaton energy density has been dissipated. Now, of course, the normalization of the distribution is the most relevant quantity to determine the relic abundance, but this shape, which is not thermal, is going to be a crucial ingredient to determine constraints imposed by the matter power spectrum, as I will mention briefly. This Q variable, by the way, is nothing but the comoving momentum rescaled by characteristic energy scale. So the corresponding relic abundance can be written explicitly and is crucially dependent on the reheating temperature to the first power, as well as the model parameters, and is a very well-known result. Okay, so in the case of scattering production, one can, for simplicity, focus on one particular production channel. So here it's H and U to dark matter. The amplitude in this case is dependent on the first coupling, and assuming these two particles are in thermal equilibrium, you just have to use the Fermi-Dirac and Bose-Einstein forms. The resulting distribution for dark matter is very non-thermal, despite the initial ingredients, with a tail that actually decreases faster than a Gaussian. And the relic abundance in this case for a quadratic inflaton potential depends on the model parameters, of course, on the masses, and on the fifth power of the reheating temperature and the reheating temperature only, meaning that the bulk of dark matter is being produced at the end of reheating at the reheating radiation boundary. But if you change this assumption and consider a quartic potential, then the abundance picks up a correction that is proportional to the 10⁻³ power of the ratio of the maximum temperature of the universe to the reheating temperature, implying that in this case, dark matter is being produced at the inflation reheating boundary well before the completion of the hot Big Bang. And so you can get a very different result with the same production mechanism, depending on the details of reheating. And of course, the complication doesn't end there, because I mentioned thermalization is not instantaneous. And so initially, the H and U are not in a thermal state. They have a distribution that scales with the 3½ power of the momentum. And so one can compute the phase-space distribution and the relic abundance of this non-thermal component of the dark matter. So it's also a very non-thermal shape. Quite complicated expression for the relic abundance, because now this abundance depends on the thermalization time scale. Okay, so you get these phony powers. But the crucial thing is that depending on the branching fraction of the decay of the inflaton into neutrinos, this mechanism can actually dominate over thermal production even for a quadratic potential. So given the fact that I'm running out of time, let me now very quickly discuss gather all the results to explore the allowed parameter space for this very simple model. So the relic abundance of dark matter coming from scatterings is going to be then a function of the coupling, the reheating temperature, and its mass. These curves are curves of relic abundance equal to the observed one. And so for a given inflaton to neutrino branching fraction, some part of the parameter space will be dominated by thermal freezing, and hence making a dark matter relic of the end of reheating, while some other part is dominated by non-thermal freezing, making dark matter a relic of the end of the inflation. This exclusion region in blue corresponds to the limit on the lifetime of these particles given by gamma ray and neutrino constraints, emphasizing the 130 GeV Fermi line and the PeV ice cube event. Just to note that for a given signal, you can translate it into a reheating temperature and also to a production mechanism. And on the right, I'm showing analogous limits for the decay of the inflaton, highlighting the reheating temperature in this case. So note that even for out of equilibrium dark matter, indirect signals can give relatively powerful constraints, not only on the abundance, but on the dynamics of the early universe. And we note that these constraints are operating on the high mass range of the figure. For low masses, one needs to look for a different signal. And one possibility is to explore the effect of light-dark matter on the matter power spectrum. Now I don't have to spend too much time here because Jeremy already introduced this suppression of structure for light-dark matter, mentioning that there is a bound of 3 keV for a thermal warm relic. Okay, so in this case, the best constraints on this suppression by relativistic dark matter particle come from Lyman alpha observations. And so just to emphasize that this result corresponds to a relic produced through thermal freeze out for a non-equilibrated dark matter. then the free streaming scale will not only depend on the dark matter mass, but also on its phase space distribution. So Jeremy mentioned using class to compute the corresponding transfer function. What we found was actually that if your phase space distribution is sufficiently well behaved, there's no need to use any numerical code. You can just do a simple linear computation. And one can translate the warm dark matter bound to any essentially out of equilibrium scenario by simply doing a rescaling procedure just by computing moments of the corresponding phase space distribution. And so for the direct decay of the inflaton into dark matter, what we obtain is that the Lyman alpha constraint translates into a constraint that looks like this. So it's actually constraint that depends on the reheating temperature, becoming more severe the lower the reheating temperature is, because you're producing dark matter too late, so it can be very relativistic during structure formation. So you have to be careful with that. For thermal freezing production, the bound looks very much like the warm dark matter bound, except that you gain an order 1 factor. And for freezing coming from not yet thermalized relics, the bound can actually be relaxed, because now you're producing dark matter very early, and so it can be very light and still be compatible with power spectrum constraints. So this is my last slide showing precisely the change in the allowed parameter space. For scatterings, Lyman alpha is ruling out a sub KV range depending on the production mechanism. So for the thermal one, you don't see anything interesting. There is a little bit of an allowed region for non-thermal production. While for inflaton decay, essentially Lyman alpha is excluding all of the parameter space except for this triangle of high reheating temperatures and relatively large dark matter masses. Thank you, and sorry for the technical problems.
Okay, thank you very much. So if you have any questions, please turn on your microphone and speak up.
Do you have any comment on the relation, similarity or difference compared to the Gravitino in the gravity case?
For the gravity, well, yes. So for the Gravitino, it depends a bit. So the usual, let's say, low SUSY breaking Gravitino scenario would correspond to something that is just thermal freezing, essentially, because I mean, you can produce it. You will produce it always from particles in thermal equilibrium at the end of reheating. So there's really not much difference in that regard. So the parameter space would look relatively similar. But it depends. So it depends on what the scale of supersymmetry breaking is. So if you have a very high scale SUSY breaking, then you can have a very cross sections that are very sensitive to the center of mass energies. So if you hide your your supersymmetric particles above the inflaton mass, for example, your cross-section scales like the 6th power of the central mass energy, and essentially, no matter what you do, you're always going to produce your dark matter particle at the end of inflation. So in that sense, all the parameter space will be covered by the orange region, so it would be non-thermal. But the Lyman alpha exclusion looks, it doesn't change that much, really. So and of course, you would lose this region because the Gravitino in that case is protected by R parity, so it's stable. You can also make an almost one-to-one comparison with extended supersymmetric scenarios like the mu from nu SSM, in which case you also add a set of right-handed neutrinos, and in that case the model looks very much like this one. So in fact, you can map it. You can see that one as some sort of a UV completion if you make your Yukawa couplings sufficiently big. But yeah, you can make a comparison. It's just it depends on how you embed in the UV these sort of minimal setup. Sorry, I didn't have the time to show it because of the problems at the beginning.
Thank you.
Yes.
Okay. Any other questions or comments? Okay. So if there is no more questions or comments, let's thank Dr. Garcia again. Thank you very much.
Okay.
Okay, so this is the end of this paragraph session. So please have some rest, and there will be following session on experiment from 5:20. So this is it. Thank you very much.